Okay, we're going to go ahead and get started. Good morning, everyone. Welcome again to the Introduction to Copper and Copper Alloys webinar. I'm Carly Rogers. I'm the Marketing and Education Manager for CAPSA. We're really excited to welcome Jim Michel, the Manager of Technical Services for the Copper Development Association. Jim has worked in the metals and corrosion industries since 1973, including the copper and brass, zinc, and steel industries. He has held positions in research and development, technical service, product development, market development, and sales development, as well as has operated his own metallurgical consulting business. Additionally, Jim taught metallurgy courses for ASM International for 10 years. He joined the Copper Development Association in January 2007. He'll answer your questions at the conclusion of the presentation. Just submit your questions using the Questions tab on your webinar toolbar, and we'll get to those at the end of the presentation. You will receive a link to the slides and the recording of the webinar. You'll receive a webinar evaluation about an hour after the presentation, and then at the end of that, once you complete the evaluation, you'll receive a link to the slides for today's webinar, and then the recording will be made available either today or tomorrow or maybe early next week. So be looking for that. With that, I'd like to turn the presentation over to Jim Michel.
Good morning. Can everybody see the screen?
1 second, I'm about to get there. Okay.
Show my screen.
Yes.
How about now?
Yep, and we see it.
Okay. Well, good morning, everyone, and thank you for joining us for this webinar entitled Introduction to Copper and Copper Alloys, and I'm pleased to be working with CAPSA on this. I'd just like to introduce CDA, if you don't know it. We're a not-for-profit trade association headquartered in New York City that provides technical, market development, education, and support services for the U.S. copper industry, with an overall vision toward positively influencing the use of copper and its alloys in today's society. I'd also like to note that CDA at the end of last year celebrated 50 years of service to the copper industry. So we've been around for a little while. Anyway, we'd like to talk about, in this particular presentation, this is fairly basic copper information. However, we'll touch on some history of copper over the ages very shortly. We'll talk about basic copper properties. Then we'll go into some production information about how copper is produced. We'll talk about how do we get properties of materials, copper materials, when we process them. We'll talk about alloy families and UNS alloy numbers. Then we'll talk about typical uses of selected alloys within the copper family. And then we'll have a summary and questions. So to begin with, let me go through with this chart, and I'm sorry it's a little fuzzy, but we stretched it. The CU is copper, and this is a timeline from when copper was discovered and first used to the present day. As you will note, copper was discovered and used approximately 9,000 BC. So copper has been used for about 11,000 years. The next oldest metal is gold, which is a symbol is AU. That's 4,000 BC. And then the alloy bronze, which was discovered accidentally around 3,000 BC. So you have a copper and bronze age. Iron was discovered approximately 2000 BC. And steel, or what we call steel these days, which is iron with carbon, was developed or discovered around 700 BC. Things like nickel, aluminum, and titanium were very recent discoveries, and our ability to make those into pure metals have been very recent. So we're working with a very old material. The name copper. Actually, let's talk about the symbol copper. Cu comes from cuprum, which is a Latin word for copper. This is a foreshortened version of a longer phrase, generally that is Aes cyprium, or metal from Cyprus. In Greek, which at those times Greek was a very popular language, copper was chalcos, or so you had cuprum in Latin and chalcos in Greek. In history, this period is called the Chalcolithic period, and literally that means the copper stone period. And if we look back at 9000 BC, the discovery of copper at that time were literally stones. It was called native copper and was then hammered out into useful objects or decorative objects. Excuse me. On the periodic chart of elements, copper is highlighted here, but it is in the transition series of elements near nickel and zinc. But if you look vertically in that group, just below it is silver, and further below that is gold, Au. So it's chemically similar to the other noble metals, silver and gold. In copper properties, these are basic copper properties that we put at times, but we don't think about when dealing with copper in a general sense. The symbol, obviously, we talked about is Cu. The atomic number, which was on the chart, was 29. Atomic weight, 63.5. Standard state, it's solid at room temperature. The color, and we all know copper is copper color or reddish, and metallic in sheen. But general properties, it's very ductile material. It's malleable. It's able to be formed into all kinds of different objects and shapes. It has high thermal conductivity, one of the basic reasons it's used. It has very high electrical conductivity, and that's another basic property that is used in many of the applications. It's easily alloyed, as we'll see later in some of the alloy discussion. It has very good corrosion resistance and is used and has been used over the ages in many applications, including seawater applications. It's readily available. We've been mining it or finding it for 11,000 years. There's still a ready availability of the material. It's recyclable. You can take copper that is in one form or another or one alloy these days, melt it down, make new material. Very recyclable. And a new property, but an old property, antimicrobial. And we'll touch on that a little bit as we go along. Let's talk a little bit about the production of copper in a general sense. Normal production starts with mining. You'll note two of the illustrations or photographs here are mines. Up to the upper left and the bottom center are open pit mines for copper. The other way of mining is a shaft mine or deep mine. That is generally not in use these days. A vast majority of copper is produced by open pit mining. Once it's mined or brought out of the ground as ore, it's crushed and processed in various ways and separated out from all the miscellaneous materials that are there. And finally, it comes out, as the illustration on the upper right shows, a copper cathode, which is pure copper. That material then goes into a wide variety of applications or uses, and I have charts that will show the process flow for copper production and reuse. Let's talk about the types of ores. There are two basic types of copper ores, and these are examples of those types. Sulfide ore, where copper is tied up with sulfur. These are bornite, chalcocite, or chalcopyrite, for example, or oxide-type ores, which are lesser available. Malachite, azurite, or chrysocolla. And you see artist examples of what they look like. Here is this is a chart that builds, but we start with copper and copper ore in a mine. We move from that to taking it to a smelter. And in a smelter, the word starts with an S. You're taking sulfur out of the ore or the concentrates that go into the smelter. Anytime you see smelter, you're taking sulfur out. Then it goes further into processing where it can go through solvent extraction, that's SX, and you end up with a pure copper or refined copper. In refined usage, once you have a refined copper, it goes into a wide variety of production facilities, fabrication facilities, that end up making a wide variety of products. They're not final products, they're intermediate products. Products that you at the Copper and Brass Service Center Association sell out of your service centers. Wire, rod, sheet, strip, plate, possibly foundry materials. Here we have wire rod plants, wire mills, tube mills, rod mills, brass mills, or sheet mills, where we make sheet, strip, plate, foundry materials, where you end up with ingots for casting. At each of these places, and these diagrams show scrap at the bottom or runaround. This, all, as a title shows, it talks about recycling as well. Once we make all of these different fabricated products, which are called semi-finished, we have beyond that, and they go into product supply into manufacture of a wide variety of things. We copper are used in all of these areas of construction of types of equipment or material things, construction equipment, electrical and electronic equipment, industrial equipment, transportation equipment, that's cars, trucks, boats, trains, etc., airplanes. General consumer goods, what you buy at the store, your iPhones, things like that. And other uses like mixers and so forth. And, applying in your house. All of them use a wide variety of materials. These then finished products are generated from this manufacturer, and they go in, this is very highly stylized, but they go into what's called the copper ore that's in use, or copper usage we have. Now, some of these products that are used, like a stove or a range in the house, have a lifetime. Many of them are used for 10 years. Some of them are used for 20 years. A car can be used for a long period of time. But think about a home or a building. They have copper wiring. They could have copper and or other alloys in that building. That building could be used for 100, 200 years. That's the reservoir of copper in use. Some copper objects like pots and pans and art objects are used for centuries or millennia. At some point, there's an end of life, EOL. The products are thought to be used up, or somebody wants them renewed. So they go to different points where end-of-life management is done. I'm not going to go through all these acronyms that are here, but all the yellow boxes talk about end-of-life activities. But you'll also note a lot of the life management activities circle back into scrap, which then goes all the way back in the diagrams to remelt and reuse. So copper is readily reused on a continuing basis. Well, let's get a little closer to production in a sheet strip plate tube mill. And let's talk about melting furnaces. Some of these you may have seen. These are just examples. A large furnace that is often used in copper production of basic copper materials, not often copper alloys, but a reverberatory type furnace, where the A and B areas on this diagram are actual melted copper materials. The E is where the fire comes in here, the heat, and the G is the stack, or where the gases go out. You have a collection point, F, for any fumes and so forth. This is just a very basic diagram. This can house a reservoir that's absolutely huge as far as copper material. And of course, you cast out of this. Other types of furnaces generally are the electric arc melting furnaces. Here's two different types. There are other types as well. Most of these have a hood that covers them in melting and during part of production. In these, it's a smaller vessel and smaller production lots. You can make brass in this and change the edge. You can make copper nickel in these. You can make a bronze, a variety of other materials. And in that way, you're only making a relatively small amount, whereas in a reverberatory furnace, which is much larger than these, you would be making 120,000 pounds at a time. So the volume is different. these are schematics, and they just are examples of production processes. The top illustration shows a continuous production process. And by this, I'm trying to illustrate if you're making a certain type of product, and this can be good for a wire or a strip or a rod or other materials like that, you basically cast, do some hot working. There's a hot section. You cool it down. You do some cold working on it, and you cut the product off, and it's a single flow system. Very efficient, but you have to be very focused on what you're making. A vast majority of sheet and strip and plate is made in the bottom process, where you make a large amount of material. You have big size strip or sheet. You do various rolling processes. You anneal it or soften it. Then you cut it down to medium size. You do other processing, and you get smaller size strip. You may do some heat treatments or cleaning. You do slitting and packing, and then transporting. So it's an involved process. Many of the big sheet mills that you would plate or strip from is the bottom process. Okay, let's talk about development of properties within a material that's being processed in one of these mills. Let's talk about plastic deformation and temper. Metals are made up of crystals. In metallurgy, they're called grains. Deformation of the crystal structure causes internal stress. This is seriously important. Internal stress in the crystals are developed from rolling, drawing, or other processes, and a temper is determined by various processing parameters. Annealing allows you to relieve all or some of the stresses that you develop in the processing materials. In plastic temper, again, metals are polycrystalline materials. Here's a schematic of ongoing rolling of a strip. The elongation of the grain structure or crystal structure during cold rolling ends up in developing a preferred orientation or flow of the grain structure, as you can see as you move to the right on this diagram. But if you squeeze down on the material, it is strengthening, or the internal stresses are becoming greater. So you can develop various temperature. Looking at it in an overall sense, you work with tempers, or your customer specifies a temper. Quarter hard, half hard, hard. The tempers are on this diagram, and they're noted at the top. Soft, there's no real temper there. But on the far right, you see on the top, on the bottom is a corresponding reduction in thickness in percent. Well, if you're soft or the material is soft, there's no reduction. If you're quarter hard, you have about a 10%, 12% reduction on final rolling to give you that temper. If it's spring, you have about a 61% reduction between the preparation size and the final size to give you that spring temper. Now, this is a very interactive diagram so that if you are decreasing the thickness by a great deal, such as a spring temper, the elongation of the material will go way down. The tensile strength will increase, and this is a RAS, so it's not going to increase tremendously, but it goes up from 40,000 to about 82,000 tensile. So the tensile strength, yield strength increases, the elongation decreases, the temper, or the increases, or the reduction in thickness. This is how tempers are developed in processing. It's generally at the final process point. And here's a table which talks about or shows both rolled sheet and drawn wire, the reduction in diameter for wire or a reduction in thickness for sheet gives you the temper. And like I said, this is the last rolling or drawing of the material before finished size that gives you the temper. All right, let's talk about copper alloys. Well, I just went through. Copper alloy designations are actually unified numbering system UNS alloy designations. The UNS system was begun in 1974. And originally, there were only 3 numbers for an alloy. Now, the numbers all start with a C for copper, being a copper alloy, plus 5 numbers. So the original 3 numbers that were used for alloys back starting in 74 have been expanded. And we'll see how that looks in a few minutes. Wrought and cast copper alloys are all included in this system. CDA, Copper Development Association, administers the UNS copper alloy system for the United States. And I just ran some numbers that we have 829 copper alloys registered in the United States. And just for information's sake, there are 479 that are approved antimicrobial alloys. Well, in making a copper alloy, you add something to copper to make that alloy. And here's a nice little diagram which shows you some elements that are added to copper to provide various properties. Let's go to the left. For color, you can add zinc. Copper and zinc is brass. The more zinc you add, it changes from a reddish color, copperish color, to a golden color or yellow. If you add nickel to copper, it can change from a copper color to a pinkish color to a golden color to a white alloy or silver colored alloy. For other properties, for machinability, normal material would be to add lead. There's also zinc, which adds some lubricity for machining, tellurium, and so forth. For strength, you can add titanium, nickel, zirconium. Zinc is a strengthener as well. So there's lots of different materials that can be added. Sometimes you add a multiple group of alloying elements to get an alloy itself. Let's go into what the wrought copper alloy families are. Basic definitions. If you have a number that is C100 with two numbers after that to C150 with two numbers after that, you're in the commercially pure copper range. There's small additions of a variety of elements that are there or not there that give you those alloys. In the C151 to C199 range, with the other two numbers, these are age-hardenable copper alloys. They can have a variety of other elements. I've given some examples: cadmium, beryllium, chromium, iron, but there's a variety of others that can be added there to get hardenable copper alloy. Still, majority copper. If you go to the C2 and 4 numbers series, like C260, XX00, it's a brass. That whole series are brasses. If you go to the group C3 with 4 numbers after that, these are copper, zinc, lead alloys, leaded brasses. If we go to C4 and 4 numbers, the 400 series, these are generally copper, zinc, tin alloys, or tin bronzes, or some tin brasses they're called at various times. The C5, 50,000 series, if you will, are copper tin alloys, or copper tin lead alloys, leaded phosphor bronzes. And just as a side note, the early bronzes that I had on the timeline at the beginning of the talk were copper tin alloys. And so these are the oldest, other than pure copper, materials in use. And there are still art objects that are in museums from ancient times that are ancient bronzes, and they would be in this class. The C6 with 4 other numbers would be the copper aluminum or copper silicon bronzes. It's sort of split into 2 groups. And then C7 series are copper nickels for about the first half of that numbering system, and copper nickel zinc series are nickel silvers. We'll talk about examples here of each in a moment. Cast copper alloy families. Well, these are sort of a smaller group. In the C800 to 811 with 2 other numbers, these are commercially pure coppers. In the C813 to 828, they're generally very high copper alloys, 95 to 99% copper. 833 to 899, you have copper zinc alloys, brasses. They can contain a variety of other elements. They can be leaded brasses, silicon additions, and so forth. And the C9 4X series are other alloys, including tin bronzes, aluminum bronzes, and the copper nickels in that group. These are all casting alloys, and they would be used in foundries of various types. Well, I've been asked to go through a few examples and uses of copper alloys. Typical uses of C110 copper. There's a lot of it used in architectural applications, building fronts, downspouts, flashing gutters, roofing, screening. But it has been used in gaskets and radiators in automotive. That's the heat dissipative properties. Electrical, bus bars, conductive wire, radio parts, switches, terminals, conducting electricity. Hardware, you have all kinds of different nails, rivets, cotter pins, tacks. And miscellaneous, you have anodes to plate with, chemical process equipment, kettles, pans, printing rolls, and we'll look at those in picture form here. In the upper row, you see some architectural uses. And in the upper right, you see a screen. In the far upper right, you see a bus bar and interconnect on that. In the second row, there's a radiator, second to the left. In the far right, there's a board from an electronic piece of equipment. And in that board, there's usually some copper foil. So it's produced very thin and sandwiched between layers of these boards. Obviously, electric wire. A lot of that used, that's pure copper. Kettles and pots. What you'll note in the bottom row, there's a vat. This is a still. You can also go into breweries and see copper as brewing equipment. And then on the far left, here's a rotor in a motor, but it also has copper windings in that motor. So motors, electrical equipment like that, very big users of 110. Alloy 260, cartridge brass. All kinds of architectural uses, radiator uses, lots of flashlights and so forth were made out of those materials in the past. Plumbing goods, fasteners, screws, eyelet parts. The reason it has its name cartridge brass is ammunition, which is on the lower right in this illustration or this photo. The cartridges are made out of brass, this brass, 260. And it's been a use for it for a long period of time. Obviously, there are a lot of other uses, many of them decorative. You have lamp parts, architectural uses. But if you look at the middle left, that's an outlet and switches in your house. That has 260 brass in it. Door hardware and railings and tubes and kick plates for your doors. Faucets and other decorative pieces are made out of 260. I added 360 because of a request. This is free machining brass. Essentially, 360 is 260 with added lead. And this is primarily produced in rods and tubes to be made into a variety of products on screw machines. But it can be made into gears and pinions and things like that as well. Here are some examples. Most of these have been machined into shape or are machined into shape. So you can see there's a wide variety of these, and the faster they're made, the more economical they are. And the lead adds an easy capability to machine these parts very quickly. Phosphor bronze 510, which is basic phosphor bronze. It's used in architecture in various ways. Bridge bearing plates is noted. Hardware, you have all variety of different things from cotter pins, sleeve bushings, springs, switch parts, fasteners. In industry, there's textile machinery, welding rods, chemical hardware. And here are some pieces and parts made out of phosphor bronze. Little pieces that you, in the mid-right, you see springs. There are springs and connectors made out of phosphor bronze, and connectors in the middle, for electrical and electronic uses, and the upper middle as well. These products are used, and you never see them, but they're there, and phosphor bronze has a little more strength, and it's used in these applications. Copper nickel, alloy 706, which is 10% nickel. Primary industrial uses are condensers, condenser plates, distiller tubes, evaporator and heat exchanger tubes, ferrules, saltwater piping, saltwater heat exchangers. I didn't put down, but it's being used or beginning to be used in many applications for antimicrobial applications. Here are some applications. The four to the right are all saltwater or seawater applications for corrosion resistance. You have a ship on the upper right. You have a power plant, but or a plant that's near the ocean. You have pipes and various fittings and fixtures in the bottom center, and somebody's welding these materials on the lower right. But on the left, there's an outlet or a switch, and we have those in our offices. These are copper nickel, and they're made out of made for the antimicrobial market. And railings for a wide variety of applications, and those are antimicrobial, and 706 is very good for those. Now, alloy 752 is called nickel silver. And many of you may wonder, why is this and the series of alloys that this represents called nickel silver? It's basically a copper, zinc, nickel series of alloys. But when you add about 18% zinc and the equal amount of nickel, the nickel turns it white. Original name for these alloys was German silver, and these were developed in a general sense in the early part of the 1800s in Germany. And they have been used since for a wide variety of applications. In hardware, they're used for fasteners and zippers, flatware, miscellaneous uses, camera parts, bows, core bars, other miscellaneous, base for silver plate, costume jewelry, etching stock, hollowware, nameplates, radio dials. Let's look at which I didn't put down, I'm sorry, musical instruments. So you have a cornet in the center, which is nickel silver. You have a violin bow at the bottom right with fittings of nickel silver. You have a zipper in the bottom center. A lot of zippers are brass. This one happens to be nickel silver. And you have a clarinet in the upper left, but you have jewelry in the upper center. Eyeglass frames are made out of nickel silver. And various silver plate items or tableware items are made out of nickel, silver, and then silver plated. Well, let's look at the overall markets for copper materials. I've given you examples of where some of these alloys are used, but what are the overall market areas for copper materials? These are the figures I'm giving are from 2011, which is the last full year that we have. 2012, we don't have a full numbers yet. Building construction is the largest segment that uses copper materials in consumption, about 44%. Electrical and electronic materials and equipment are about 20%. Transportation equipment, 16%. Consumer and general products, about 12%. And industrial machinery, about 7.5%. So that's about 5 billion pounds of copper alloys used. Let's look at it another way. As far as products that you would see go through a service center or someone would use. Wire and cable, copper wire and cable, or wire and cable containing copper, about 51%, greater than half. Sheet, strip, and plate, 16%. Tubular products, 14%. Rod, bar, and mechanical wire, about 15%. And foundries and powder, about 3.5%. This gives you a perspective of what the semi-finished products that are produced and sold go into, or how much is sold. Wire and cable is a preponderance. Well, I've talked quite a bit here, and thank you for listening, but I want to summarize. And I have a clever chart here, but it wasn't mine. We start with copper ore, and we end up with refined copper. We use recycled copper, make copper alloys. What do we do with that? We make plate, sheet, strip, and foil. We can use these for castings. We wire rod. We can end up with powder, rod, bar, and sections. Where do these go into? They go into transportation, consumer products, building and construction, electrical and electronics markets, and industrial machinery. Well, let's look at it a little further. The copper also goes into paints, tubes, brakes, bearings, food supplements, nutrients. We all need copper in our vitamins or in our food. Screens, sheathing, gears, coins. Look at your coinage in your pocket. The silver-colored coins, dimes, nickels, quarters, they're copper nickel. Vessels. We saw some piping used in onboard ship. Brassware, locks and keys. Fungicides. Our crops are better because we spray some copper sulfate on the crops to prevent mold and mildew. And lastly, we have all kinds of different things that end up being used. Roofing, cables, motors, connectors, wiring, sprinklers, heat exchangers, taps, meaning faucets, valves, fasteners, radiations, meaning heat exchangers of some type, fittings, electric hardware or electronic hardware, and circuit boards. Well, that's a quick summary and a quick overview of what we do with copper and copper alloys and where they come from. Thank you for your attention. And I believe Carly will come back on, and we can take some questions. Hello. I'm ready for questions if that's possible. Oh, well, our host got disconnected. She will have to call back in, I guess. But please submit your questions as soon as possible. We'll do as much as we can right now to answer a few questions in the time remaining, but we will also be able to answer questions offline.
Jim, I'm here.
Okay.
I'm so sorry, everyone. I accidentally got disconnected. I went to go switch over and hit speaker instead of mute. I apologize for that, but that was a great presentation. I heard it all the way up until the very end.
Well, thank you.
All right.
Do we have any questions?
Let's take a look here. We do have a couple of questions, and again, everyone, if you've got questions, go ahead and just send that into your questions toolbar, and we'll get those answered by Jim for you. All right, let's take a look here. We have not a question, but we have a comment, and they just want to say thank you for making the industry in which I work a little clearer. So thank you for that. It's always good, a little reassurance there.
It's always good to know that there are all the things that are going on in the industry. So
yeah, and it's another thank you for the information. It's much appreciated. So good. We're glad to see that people found the information very worthy. So let's see. Can we refer customers directly to the CDA for guidance in selecting alloys for design?
Yes, that is true. We have a technical question and answer program. If it's for architectural purposes, we have an architectural and plumbing groups that will answer questions, but we also have other technical people that will answer questions. Is this the right alloy for this particular application? That type of question. Or if you're asking whether a certain brass should be used versus another brass, we could probably address that as well. If you're talking about corrosion issues, especially in certain instances, we have information on that. So we can address those and answer many questions, yes.
Okay, good deal. It looks like you will get a copy of the presentation afterward. I think I said that there's going to be a survey that's going to be sent out about an hour after. So here at about, well, it's 11 o'clock Central my time, so about noon or wherever everyone is. You'll be getting that survey, and then at the end of the survey there's going to be a PDF version of the PowerPoint, and so you'll be able to see that. It looks like we had another question just come in. Of the areas you mentioned, which do the Copper Alliance see as the most under threat from substitution?
Well, at the present time, well, over the years, conductivity applications have been under threat. In other words, using other materials like aluminum or other alloys or metals to conduct electricity. Some of those have fallen by the wayside in the distant past, such as home wiring made of aluminum. That's been disallowed, but there are other uses of aluminum wiring, and they're being looked at in all kinds of applications right now. But architecturally, when copper alloys are higher priced than they are presently, people find a way to use other things, if you will. So we're always under threat in one way, shape, or form. But yes, we have other things going on, yes. And thank you for the question.
Okay, looks like we have a couple more questions coming in. What, if anything, is being done to promote the antimicrobial properties of copper to the marketplace by your group?
Well, that's a very good question. And we have worked for well over 10 years quantifying, registering, and promoting the use of copper and copper alloys as antimicrobial materials. This has been a very difficult process. We had to go to the EPA for registration, and that is not an easy thing. As I mentioned earlier, there are 479 alloys registered as antimicrobial materials with the EPA. They will not let certain alloys be registered because of alloying elements like lead. So there's groups of alloys that cannot ever be registered. So we've done a good job there. Two of our people are presently at a patient safety conference with hospital individuals in New Orleans right now, promoting the use of copper alloys in the antimicrobial area. We have also participated in and helped publish the final results of a hospital study at 3 U.S. hospitals that indicated in the final result that if you put copper, and these were in the intensive care units of these 3 hospitals, if you put copper in these hospitals, in the patient rooms, and that's the way we did that in these studies, you would have, the study showed it, you would have a 58% less chance of getting a hospital-acquired infection if you were in a copper room. Now, that's phenomenal. Nothing else can say that. Copper and copper alloys are basically registered as solid disinfectants with the EPA. So that's, and we're promoting primarily to the healthcare and hospital environment at the present time. But the building environment, public buildings, transport, and other areas are being talked to as well. So this is a growing activity, and this is not just only in the United States, but around the world in the Copper Network, or Copper Alliance. There are installations in France, in Ireland, in England, in Greece, in South Africa, and all over the globe at present, but it's just beginning. And if you want more information on that, you can go to antimicrobialcopper.com as a website.
Okay. What about the future outlook of leaded bronze? Can you tell us anything about that?
In what way? If it's for machine products like screws and stuff like that, it's probably going to be used forever. If it's in touch surfaces or applications where you have water or potable water in the flow, it's not going to be used there. So there's going to be a restriction on many alloys that have lead in them because of the lead. But as far as machine parts or machine products that are used in a general sense, I don't think it'll ever be fully restricted. So.
Okay. We have kind of a long question here. It might be kind of multiple parts. So we have someone asking if you can tell us about any developments of the copper industry in Africa. Do you know if it's increasing? and where, and then are American companies obtaining copper from this region of the world, and how do the restrictions imposed by the Dodd-Frank Act impact American companies who are trying to obtain copper from Africa?
Well, okay, let's talk about, in general, the mining of copper in Africa. And let me back up a little bit. There's copper and copper minerals on every continent in the world. So when people talk about we're running out of copper, that is not true. There's plenty of copper worldwide. That being said, let's talk about Africa a little bit. There, in the not too distant past, some new mine was opened by Freeport-McMoRan Copper and Gold in South Central Africa. Now, it's hard, and the countries keep changing names over there a lot. I have to say that. But north of South Africa, but not too much, there's a belt of mineralization that has a wide variety of mines in it. So this is in the general South African area. That's where most of the copper and related metals are mined. And there's plenty of material there. The biggest problem in that region is political, as you can probably imagine. But the usage of copper in Africa is, I'd have to say, more limited than in other regions of the world. I think I'll leave it at that.
Okay. Well, I think if anyone has any further questions, we've got, Jim's contact info up here. Feel free to shoot him an email or give him a call if you, think of any questions, after we get off the call here. But just want to thank you again, Jim, for, your time this morning and presenting us the Introduction to Copper and Copper Alloys. It was very informative presentation, and I apologize again to everyone for my technical difficulty. That's the first time that's ever happened to me before, so apologize for that, but just want to thank everyone for joining us today. Like I said, following today's webinar, you're going to receive an online evaluation. At the end of the survey, just click the link and it will take you to the slides of Jim's presentation. And again, he's available if you want to reach out to him for any questions. And just stay tuned on CAPS's website, copperbrass.org, for the webinar recording. We're going to get that up as soon as we can. So just want to thank everyone again, and